Hello there. James Webb Space Telescope has so sensitive mirrors it could theoretically detect a bumblebee on the moon. But in order to do that, Webb must first calibrate all of its scientific instruments and mirrors after reaching its destination at Lagrange 2.1.5 million kilometers away from Earth. Webb begins gathering its first set of scientific observations after its commissioning process is complete, roughly 6 months after launch. The initial few weeks of commissioning includes Webb's unfolding process, which is already completed. The mirror system that collects and focuses light for James Webb is referred to as the optical telescope element, OTE. It has a three-mirror anastigmat design consisting of primary, secondary, and tertiary mirrors. A fourth flat mirror, called the fine steering mirror, FSM, is used for point stabilization and very small offset maneuvers. The effective focal ratio of the OTE is f20, and the effective focal length is 131.4 meters. The mirrors are made of beryllium, which is both lightweight and very stable for temperature variations over the range of 30 to 80 Kelvin. The mirrors are coated with gold to provide high reflectivity for 0.6 to just beyond 28 nanometers. The primary mirror is comprised of 18 hexagonal segments, each 1.4 meters in diameter, which when properly faced together act as a single mirror 6.5 meters in diameter. The hexagonal shape of Webb's primary mirror allows for a roughly circular segmented mirror without any significant gaps, taking up space between the segments. The unobscured collecting area of the primary mirror is 25.4 meters squared. An opaque border around the outer edge of the primary mirror helps minimize stray light. Each primary mirror segment has actuators on its back that allows control of the 6 spatial degrees of freedom with a precision better than 10 nanometers. A 7th actuator on each segment controls its radius of curvature, allowing correction for slight manufacturing variations to ensure all 18 segments' focal lengths are very closely matched. 2 segments needed larger radius of curvature corrections than the rest, and as a result have somewhat higher surface residuals. The secondary mirror is a convex circular mirror 0.74 meters in diameter. A set of 6 actuators allows control of the mirror's position and orientation, similar to the control of the primary mirror segments. The observatory gradually cools down to its cryogenic operating temperatures before it can safely operate the science instruments, about 40 Kelvin. Once Webb is significantly cool, Webb's NIR cam instrument is able to help determine that light is correctly following its path through the mirrors and instruments. Next is the process of adjusting each of the individual primary mirror segments through a process called wavefront sensing and control. The NIR cam instrument measures any imperfections in the alignment of the mirror segments that prevent them from working as a single mirror. In order for Webb's primary mirror segments to act as a single optic, each of the 18 hexagonal segments must be aligned to within a fraction of a wavelength of near-infrared light, mere nanometers, or about 10,000 times thinner than a human hair. Telescope alignment of both the primary and secondary mirror is completed about 4 months after launch, and only after 6 months, Webb can start conducting routine science operations.